This is 20th November 2010 theory exam. First question, if the voltage and current are known, what two other factors are required to calculate the power consumed by a three-phase motor? So three-phase power is IL/VL root-free power factor. So they're testing your knowledge of the formulas, so they're looking for root-3 and power factor as one answer. You can do it with phase voltages and current. So phase voltage times phase current times power factor times 3 will give you the same answer. I would be looking at root-3 and power factor. 2. What factors are required to calculate the power consumed by a single phase? So single phase power is our voltage times current, or V squared over R, or I squared R. So you're looking for any two of those. Easiest one, voltage and current. Power equals I times V. Direction of rotation of a single phase motor has been reversed. So we've reversed the run winding. What type of motor is this? So it's going to be a split phase or a capacitor start or a cap start cap run motor. It's going to be one of those types of motors. As soon as you see the run winding. Now this one we see we've reversed the armature brushes. So the armature, what type of motor is it? It's going to be a universal motor, sometimes called a series motor. The DC series motor can be used as the universal motor. So when we see brushes and armatures, we're looking at universal motor. When we see run winding, we're looking at these. One reason why the frame of a class 1 electrical appliance is earthed, so that the protective device operates under fault conditions. What's the other reason? So again, this comes up again and again. It's to keep the metal frame of the appliance at earth potential under fault conditions. So if there's a fault, if it's nicely earthed, it will stay at 0 volts and no one's going to get a shock. Two factors determine the severity of electric shock upon the human body. So the voltage, the current level, the shock current. The duration is going to affect the severity, how dry the skin is, and the current path that it takes through the body. We've installed some protective devices. The devices have a fault duty lower than the prospective short circuit current. So the prospective short circuit current is the maximum current that system can deliver under fault conditions. And if our protective device has got a fault duty lower than this, then we're going to have all sorts of problems. We're going to have flashovers because we've got inadequate kVA rating of the protective devices. It's going to damage the protective device. It can't contain the level of fault current. That's the basic crux of the matter. It can't handle that level of fault current. If the fitting doesn't have that fault duty, if it's not enough, if it's lower than this prospective short circuit current, then we're going to cause damage. It's going to be a fire hazard and damage to the equipment. So we need this fault duty higher than the prospective short circuit current. Carried out a test on a low voltage final subcircuit electrical installation. The test result value was 20 mega ohms. Now seeing 20 mega ohms, what type of test? I would say that was an insulation resistance test. The test was carried out with a multimeter that had the required function scales. They've thrown this in a lot, that using a multimeter to do insulation resistance, and they get around it by saying that it's got the required function scales. So it's got that 500 volts capacity. So don't be fooled when they just say multimeter. What function was selected? So insulation resistance test function, 500 volts DC. I would be putting both of those in actually to cover the full answer. What range was selected on the multimeter? So either the mega ohm range or 500 volts DC. I would be putting the 500 volts DC. What test result would you expect if there's a MIMS element? So there's that MIMS again. Alarm bells ringing. It's not the 1 mega ohm. It's this 0.01 mega ohms or 10,000 ohms. Now, the main reason why interlocks are used in star delta starter, and we don't want the motor being in star and delta at the same time, So we have mechanical interlocks that stop it going into both conditions. And so we've got G. I've lost myself here because there's an alternative answer there for circuit resistance test. It could have been a circuit resistance test. So there's G, to prevent the star and delta contacts closing simultaneously and causing a short circuit. So we have that interlocked to stop that happening. H, we've got a we're going to find the power factor. Three-phase printing factory with mainly motors. So the power, we've got 30 kilowatts, 406 volts, 57 amps per phase. So the power is equal to √3 VI power factor. So what they've done there is transposed for power factor, and the power factor is the power, which is our 30,000 watts, divided by √3 times 406 that we're told here, and our 57 amps we're told here. With this calculation, make sure you put brackets around these when you do in the calculator, or do this calculation first at the bottom, find the answer, and then do 30,000 divided by that answer. And you should get that 0.748. In relation to HRC fuses, define the term cut-off time. Now with their answers here, they've put every answer that you could have. I don't agree with all of those. I would say it's the pre-arcing time. So it's the time taken to melt the fuse element is what I would consider the cut-off time. The total clearing time is the total time it takes to interrupt flow of current and extinguish the flame. So there's going to be some arcing and after the pre-arcing time, and so the total time is from when the fault occurs to when it's extinguished. What's the purpose of slip rings on a wound rotor induction motor or slip ring motor? They connect to the external resistance, to the windings of the motor. So the windings will go to the slip rings will go to the external resistance. Then we've got our MEN system here. You're carrying out earth fault loop impedance tests on a single phase socket outlet. This is what we're testing. Now what they're asking you to do is list the earth fault loop impedance in terms of all the components of the system. Now, usually they ask you to draw it on here, which is much easier. This is a bit of a pain in the arse. You have to go through all of the connections. So going from the earth connection there, we've got the final sub-circuit earth conductor, which goes to the main earth bar, which goes to the MEN link, this MEN link, which goes to the neutral bar, and then the consumer's neutral, and then the distribution neutral to the star point of the transformer. Now, what I think that they've missed out the actual winding of the transformer, which is fairly important in the calculation of earth fault loop impedance, and they've gone for the white active phase conductor, and then to the main switch, and the switchboard cables, and the protective device, and the final sub-circuit active conductor. So it's our traditional earth fault loop impedance, but they've done it in words. Just realised I think I started at the wrong point there. It should have been here. Sorry about that. So this is our sub-circuit earth conductor. This is our main earth bar. This is our MEN link, and that's our neutral bar. Confusing question. So you need to list all those in order. Earth fault loop impedance test of 0.32 has been recorded for 230 volts, low voltage installation. Calculate the current, so it's a nice easy one. We've got our voltage divided by impedance, 230 divided by 0.32, gives us 718.75 amps, so a huge current because we've got a very low earth fault loop impedance, which is what we want because we want that protective device to operate quickly. MEN low voltage domestic installation is required to have a main earthing conductor. So what's on the ends of the main earthing conductor? So we've got the earth bar and we've got the earth electrode. What do we need to attach at the end of the main earthing conductor? The tags warning against disconnection. Now we've got a transformer calculation. We've got a delta star, 3-phase. The secondary line voltage is 400. The turns ratio, they've given you 2859 to 20. So if I was doing this calculation, I would take that down to 1. So I'll do 2859 divided by 20. And they've actually done it over here without showing you what they've done. That gives you 142.95 to 1. So the ratio is 142.95 to 1. And when the transformer is fully loaded, the full load primary line current is 4.37 amps, and there's no losses in the transformer. So we're looking to calculate the primary voltage. So we've got our secondary line voltage. So we need to find the phase voltage. So we're going to do that by doing 400 divided by root 3, which gives us 230.9. Because when we're looking at the turns ratio, we can only work with the phase voltages. So our phase voltage on the secondary is 230.9. We know the turns ratio is 142.95, and so the phase voltage on the primary is going to be 142.95 times that phase voltage there, which gives us about 33 kV. Calculate the full load kVA rating. So the kVA is going to be V times I times root 3, and they've divided by 1000 to give the answer in kVA. If you don't divide by that 1000, you'll just get a bigger number that you can convert to kVA anyway, to kilo anyway. So we've got our 33007, which is what we just calculated here, times our 4.37, which is our current from the question. It tells us 4.37, full load primary, and times root 3 divided by 1000. It gives us just under 250 kVA. The full load secondary line current, so we're going to use that value we just found there, that kVA, divided by our voltage times root 3. So our voltage here is 400. 400 times root 3, doing the brackets like that, 250 kV divided by that gives us 360.07 amps. Well, they've done it an alternative way there. I would stick to this, finding that current there. When the transformer was tested in a full load single phase terminal, the terminal voltage dropped to 222 volts. So when the transformer is loaded, the terminal voltage goes down because of the impedance of the winding. So that question comes up quite a lot. How much does it go down? Well, we can calculate the percentage regulation. And the regulation is the no load minus the full load, so basically how much it drops, divided by the no load. So there's our no load, 230.9 minus 222. And they've put the times 100 there. I don't like it there. I think you're better off working out that part of the calculation first and then times it by 100. So 230.9 minus 222 divided by 230.9 times 100 will give you just under 4% regulation. That's the kind of figure you want to get. If you get 50 or 100 or whatever, have a look at the calculation again. You're looking for, it's going to be a fairly low percentage regulation because the difference here shouldn't be that great. State the maximum permitted rated residual current of an RCD. So personal protection is going to be our traditional 30 milliamps. If it's in medical installation, 10 milliamps, so a lower current, more protection. If it's property, then we can have between 100 and 300 milliamps. We've got class 1 appliance supplied from an RCD. An earth fault occurs and we get earth leakage flowing through some unfortunate person's body. Why doesn't the person receive a severe electric shock? Because the RCD is designed to trip within milliseconds. So although they will get the shock, the duration will be very short, and so the severity of the shock will be decreased. RCCB is installed in a single phase. Why doesn't it operate when there's a short circuit between active and neutral in the single phase? So we've got a short circuit. Now a short circuit will increase the current, but there won't be an imbalance between the currents in the phase and the neutral, because the RCCB doesn't have any overload function. It's just looking at the imbalance between phase and neutral. In New Zealand, what type of RCD is required to be voltage dependent? Well, the portable RCDs must be voltage dependent, so that when the supply is lost, it has to be manually reset when the supply has been restored. We don't want that PRCD coming back on once the supply comes back. It needs to be manually reset. So that's why it does there. That's 2. Phase and neutral of the supply side of a single phase RCD have been transposed. Is it going to be able to detect an earth fault? Yes. It doesn't care if it's phase, neutral phase. It's purely looking at the imbalance. It doesn't care about the polarity of the supply. Full names of these. So we've had these before. Residual circuit breaker with overload and socket residual current device. We've got a new low voltage single phase supply to a domestic installation. There may be a phase neutral transposition between the distribution board and the switchboard. So the phase and neutral may have been transposed. We're going to carry out a test using a multimeter to see if we've got a transposition. State the function of the multimeter you would select. So we're going to be looking for volts. So we're going to put it on AC voltage. The range, you can say auto range or a range that will read 230 volts. The additional equipment that we're going to need a temporary earth stake and an earth lead. So this drawing on the answer isn't very good, but there's our temporary earth stake and there's our earth lead, there's our voltmeter, and we're going to test at various different points that they're probably going to ask us here. So on the previous page, use the instrument and equipment you have stated to show how testing the mains phase neutral transposition is carried out. So you need to join one of the voltmeters to the neutral bar and one of them to the live side of the switch. So there's that there. What's going to happen if transposition has not taken place? So if everything's okay, we should get 230 volts between the temporary earth and the line side of the main switch. So we should have 230 volts here because that's our phase coming in. If it's not transposed, this is. And if it's not transposed, we should have 0 volts between the temporary earth and the MEN connection. So there should be 0 volts here. If transposition has taken place, then we'll get the opposite. We'll get 0 volts here and we'll get 230 volts on the neutral, which is what we've got here. Okay, because of the transposition of the phase and neutral. The low voltage insulation is protected on the distribution supply system by a 60 amp rewirable pole fuse. What's the main reason why a phase and neutral transposition on the mains will not blow the pole fuse? Well, the pole fuse being 60 amps, it's going to take a lot of current to to blow that, so the fault current is too low to blow that fuse because the impedance of the fault loop is too high. There's not enough current to blow that 60 amp. Question 6. Lots of words. So we've isolated, disconnected and repaired a circular saw. We're going to reconnect the machine by connecting a flexible cord to the DOL and recommission the saw. No danger tags or locks attached to the isolator. The isolator has a lock-in facility. The only test instrument you have is a multimeter, but again, that has all the required functions, so it can do insulation resistance. 2 test instrument tests that you carried out to ensure the circular saw is safe to connect to the supply. So they've given you a choice of 3: protective earth conductor test, insulation resistance test, correct circuit connection test. If you're given the option of 2, I would always go for the earthing conductor test and the insulation resistance test. So they're asking you to describe the 2 tests that you've chosen there. So if you went for the protective earthing conductor, talking about ohms function on the lowest range, testing between the PEC and the frame of the motor, and require a lot less than 1 ohm. I don't know if you would lose marks if you just said less than 1 ohm, because that's what you're looking for. Insulation resistance test for number 2. So I would say insulation resistance test set on 500 volts DC. And we're looking to test between each conductor of the flexible cord and the frame of the motor and looking for more than 1 mega ohm. If you want to look at the circuit connections, so you're looking between the L1 and the frame, L2 and the frame, L3 and the frame, and we should have an open circuit between each line and the motor frame using ohms on low. We've connected the circular saw to the DOL. An instrument test needs to be carried out to verify that the saw is connected to the installation's earthing system. So not that its earthing protective conductor is okay, but that it is connected to the installation earthing so that it's functionally earthed. So how are we going to do that? We're going to select the ohms function, and we're looking for a low reading, so we're going to put it on the lowest range, and we're going to test between the frame of the motor and a known earth other than the motor circuit. So we want to make sure it's connected to the earthing system, and we want to make sure that the impedance is low enough to ensure that the protective device operates. So it's not that we're looking for less than 1 ohm, we're looking for a resistance or an impedance low enough to operate the device. You can carry out an earth fault loop impedance function. So you're going to connect the tester between the motor terminal and the frame of the saw, and again we're looking for an impedance low enough to ensure the protective device operates. Question 7, we've got some meters installed in a 400 volt 3-phase 4-wire. So as soon as you see 4-wire, that must be a star connection. So these will be connected in star. We're assuming a unity power factor. We're going to calculate the total power of the installation. Now we're given the powers of the red and the blue, so we need to calculate the power of the white. The power is I times V. If we treat that single phase white phase, it says 400, but the voltage we're not going to use 400 because that's the line voltage. We know that it's star because it says 4-wire, so we're going to use 230 volts. 230 volts times 173.91 gives us just under 40 kilowatts. So the total power is going to be all those 3 added up. That's the 60 from the question. There's our 39.99 from our calculation there, and 82 from the question. Gives us 181.99 kilowatts. Second part is a little bit more tricky. We're going to calculate or determine the neutral current. So we're going to determine it by graphical means. We need to find the currents that are in the blue and the red phase. So we're just going to divide the power divided by the voltage. Again, we're using 230 because it's star connected. So we get 356.62 in the blue and 260.89 in the red. Now there are a number of ways of determining this neutral current. The way they've chosen to do it is to show one of the phases horizontal and the other two phases at 60 degrees. The angle there is 120. That's our out of phaseness between the three phases. So to find the neutral current, we draw one in phase and we draw these other two at 60 degrees. And then the gap there to scale is our neutral current. So it's the difference between all these three phases. We'll look on the theory refresher course at different ways to calculate this. Now they're looking at quite a range of answer there between 145 and 160. So it doesn't have to be terribly accurate, but you need to have some sort of scale for your drawing. So 150 amps neutral current. Question 8, we've got a nameplate of a motor. From the information on the nameplate, state the power factor. So the power factor is the cosine theta. So the power factor is 0.8. The output kilowatt rating of the motor. Now the output is the mechanical output of the motor, and you'll find that in there, HP, horsepower. So it's 5.36 horsepower. Now 1 horsepower is 746 watts, and so 5.36 times 746 gives us 4 kilowatts. The input power is our electrical input power. So again, it's our √3 IV power factor. There is their √3 VI power factor. So √3 times 415 volts, because our input is in delta, times 852, which is our input current, or full load input current, times the power factor that we found earlier, which was 0.82. And that gives us just over 5 kilowatts. And if we look at those, that looks about right. 5 kilowatts in electrical power, 4 kilowatts out mechanical power. So we've done C. D, the nameplate states that the motor has a protection rating of IP53. What is IP? So international protection, or it could be ingress protection. I always think of it as international protection. What type of protection is indicated by the first digit? So that's all about solid objects, protection against the ingress of solid objects, so how big the gap is. And they'll excuse me, let you have ingress of dust. I'm not sure if you need both of those. Probably. So it's protection against the ingress of solid objects and dust. The second digit is all about water, how waterproof it is. Protection against the ingress of water. What would be the typical connection of a three-phase 400 volt 20 kilowatt motor? So they give you a little range here: delta connection, DOL starter, star delta starter. The motor is started using the DOL with a thermal overload and HRC fuses. The thermal overload is incorporated in the DOL starter and protects the motors from overload. Briefly explain the term overload. So overload is when we get a high current, larger than the normal current, and that it's sustained for a long time to operate the overload. So it's not a huge short circuit current, it's just a higher than normal current that's for a long duration that operates the overload. Question 9, we've got a final subcircuit, single phase domestic residence. We're going to carry out some tests before it's relivened. No work has been done on the mains, earthing conductor or MEN connection. We have to carry out an insulation resistance test of all the final subcircuits. An insulation resistance test is carried out with test voltage 500 volts. Why do we need 500 volts? Well, the 500 volts is to stress the insulation beyond the peak of the normal voltage. So stress the insulation at levels above the nominal operating or peak voltage. So our peak voltage is about 329. We're going to stress it to 500 volts. Why the voltage is a DC voltage, I've always thought that it's because it keeps it at maximum. There's no peaks and troughs like AC, so it's a very good test. It gives a 500 volts straightforward DC. But they're also looking at to ensure the capacitive or inductive reactance does not influence the test result. So because it's AC, it's going to cause inductive reactance and capacitive reactance, and so they might affect the test result. So we use DC so that doesn't come into it. If I was remembering this for an assessment, I would be remembering that DC is constant and stresses it better than AC. The MEN connection of the insulation is located on the inside switchboard, and that's where we're going to carry out the insulation resistance test. Now we've got a range and a water heater, both of which contain MIMS. Again, MIMS, alarm bells, not 1 mega ohm. Carried out insulation resistance tests, and the result for the entire installation was 0.2 mega ohms. State the most likely reason why the test result is lower than the permitted value of 1 mega ohm. Now it's going to be because of these MIMS elements. So it's either the range or the water heater, or both, are going to have insulation resistance less than 1 mega ohm. So that's what we've got there. Part 2, we want to give a certificate of compliance, even though we've got 0.2 mega ohms. So basically we need to prove that this installation does comply with 3000, and it is the range and the water heater that's causing the problem. So how are we going to test that? Well, what we're going to do is we're going to take out the MEN link and the main neutral disconnected. We're going to disconnect the range and the water heater, put all the switches and circuit breakers to the on position, test between the live parts and earth. Now with this, the range and the water disconnected, we should get our minimum of 1 mega ohm for the installation without those. If it's still low when we've disconnected this, then we've got problems. We then test between the phase and neutral and earth of the water heater, and we're looking for a maximum value of 10,000 ohms. Sorry, a minimum value of 10,000 ohms. Any less than that, and there's a fault on there. And we're going to test the phase neutral to earth of the range, and again we're looking for a minimum of 10,000 ohms. So if both of those are greater than 10,000 ohms, and the installation without them is greater than 1 mega ohm, then we can say the installation is safe and complies with 3000.